Hello, everyone, and thank you for joining us today. Welcome to MEGGER's monthly webinar series. Today's topic is Introduction to Sweep Frequency Response Analysis. My name is Jamie Smith, and I'm the Digital Marketing Specialist for MEGGER North America, and I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I'll read those questions out during the Q&A segment at the end of the webinar. All webinar attendees are eligible to receive one NITA CTD and one PDH or 0.1 CEU just for attending today. You will receive that in an email within 2 business days of the webinar. And that email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again at a later date or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar during the Q&A session. Our presenter today is Robert Foster, MEGGER Applications Engineer. Also, to assist with the question and answer session, we'll have 2 panelists joining us as well. We have Dr. Diego Robolino, MEGGER Principal Engineer, as well as Bolni Naranjo, MEGGER Senior Applications Engineer. Okay, let's go ahead and get started. Thank you for joining us today, Robert.
Jamie. Good morning, everybody. So today we're talking about SFRA, or Sweep Frequency Response Analysis. And one thing I want to mention to start with is, like all tests, not one single test will tell you everything about your transformer. So it's really just another piece in the puzzle with SFRA, DGA, dielectric frequency response, winding resistance, different things you can do to figure out what's going on inside your transformer and how healthy it is. So SFRA is just a piece of that puzzle, but it's nice because it gives you a variety of information about that transformer. And really, why do we test transformers? The transformer itself is designed to withstand certain mechanical forces. But then during certain parts of its life, like early on during transportation, you can have some of these forces exceeded. Or say if there's a short circuit on there and the windings expand and contract too quickly, you can have some mechanical deviations there as well. And other things, of course, the insulation breakdown and different things like that. But basically, as the mechanical strength weakens, this transformer, it'll weaken as the transformer ages. And then as that weakens, you basically have less capability to withstand more mechanical stresses. So you have more risk of having mechanical problems, and you have a greater risk for insulation problems as well. So one nice thing, as I said, SFRA is a piece of the puzzle, but really you can see a lot of information with sweep frequency response analysis. You can see core movements, you can see faulty core grounds, winding deformations, winding displacements, winding collapse, hoop buckling, all these different things that will appear in a difference in traces when looking at SFRA results. So it's a nice one test, one piece of equipment that gives you a variety of information about the health of your transformer. So let's just start with a couple basics here. First off, this is an offline test. So you do have to have the transformer de-energized, completely isolated. You want all the bus connections off and everything like that. And then really, you're looking at the transformer as a complex RLC circuit. You have resistance in the winding, you have inductance in the winding, of course, and then you have all these capacitances, capacitance between one turn to the next, capacitance between the winding and the core and other windings, capacitance between the winding and ground. So really at the end, it's this really complex RLC circuit. But what's nice is you get a baseline or fingerprint measurement here. And then after time, you can look at these and you'll get this response. And then later on, if you run the same test and you get a different response, you know something physically, something mechanically changed inside that transformer. So it's really nice because these sweeps give you a glimpse into what's going on with the core and the windings and some taps and connections. So you can see a variety of information just by running a few sweeps on your transformer. So what are we doing with frequency response here? We have an unknown system, your transformer, and all we're doing is we're putting a signal through this transformer, through various parts of the windings, through through a winding or on a winding and measuring on a corresponding phase, corresponding secondary, and then we end up measuring the output. And then from this, just looking at the output over the input, we get a response for that transformer. And as I said, looking at the transformer as a RLC circuit, it's unique in its design. Basically, every large power transformer now is a custom design, and it will come out with its own unique fingerprint because it's got its own RLC response there. And so what you do is you look at this fingerprint, and you want to get a nice clear fingerprint on commissioning, and then later on, if something happens, you're going to run this test again and compare it and see, okay, does this new test that we did line up with our previous test? And if they do, that's great. If not, then you need to do some further investigation. And depending on where it's different, is going to show you, point to what's going wrong inside the transformer. And so I wish I could say like a hard stop, all right, 20 hertz to 1500 or to 5 kilohertz, that's all core. And then 5 to 100, that's all winding. But really you can't. What happens is you have kind of some areas where the core affects mainly the curve. And then it overlaps a little where the winding affects it as well. And then at higher frequencies you get taps and connections. So there's no set frequency range. Each transformer is different and the interaction's a little bit different. But in general, what you can say is when I'm looking at the low frequencies, this is usually an indication of the core and how the core is behaving and a little bit of the windings as well. Then when we get into the medium frequencies, you're really looking at mainly at the windings. And the first FRA devices were mainly used to look at the windings, but by expanding to the lower frequencies, we found out we could look at the core as well. So lowest frequencies, you're looking at core. The mid-range frequencies there, you're looking at the winding. And then as you get to the very high frequencies, you're looking at taps and connections and also your connections too. So if you're not methodical and you're not using consistent hardware and everything, that response can change at the very high frequencies. So connections, pretty simple. What we're going to do is we're going to use like a shielded coax cable and have a nice clamp on one side of a winding and then maybe go through the winding. And then what I'll say is that this device, SFRA, really only does one thing. It sends out an applied signal at 10 volts at multiple frequencies, and then we measure the response. And of course, we transfer this information to a computer. And then we just do this multiple times on different windings, on different parts of the transformer in order to get an overall picture of the transformer itself. So at the end, after we apply the signal, vary the frequency, measure the response, then we get a comparison here. And you get your output over your input, and you get this nice curve going across the whole frequency range. So on the y-axis here, you have basically the ratio of the measured to the applied voltage there. And then at the very top, 0 dB, meaning there was no difference in response. If it was just shorted out, no winding or anything. And then as you drop down lower and lower in the dB range, you'll see this is a higher difference in response between the output and the input there. And then on the x-axis, we're looking at frequency, and this is a log scale here, but on frequency, you're looking at pretty much from 20 hertz up to 2 megahertz there to figure out what's going on with your transformer. And then, as I said previously, at the low frequencies, you're looking more at core. Mid-range frequencies, you're looking at winding. And then as you get into the high frequencies, this is more your taps and connections. So what types of tests are we performing here? So as I mentioned, the SFRA device really only does one thing. It's not a very smart device. It just puts out a voltage at varying frequency and measures the response. What it's up to you to do is to connect this at different parts of the transformer and do these different tests. So we have 4 main types of tests here. We have the end-to-end open circuit test. We have the end-to-end short circuit test. We have the capacitive interwinding and the inductive interwinding test. So what is the end-to-end open test? What you do is you go through and you apply the signal to one side of the winding, and you measure on the opposite side of the winding. So the nice thing about this is the magnetizing impedance of the transformer is the main characterization at the low frequency. So you see information about the core, and then also as it goes up, you're going to see some information about the winding as well. But it's a very simple test. Hook up on one side of the winding, and then hook up to the other to measure it, and then just get your response. And so looking at this, you have a typical type response that you'll see. And of course, each transformer will be a little bit different, but really you'll come in and you'll have kind of like the inductive part taking over, and then it goes down. And if you're on your outside legs, you're going to see this double dip. And then on that center leg, you'll just see a single dip a lot of times. And then as the capacitive takes over, it starts to go more into the windings and everything. But generally, you look at this early part for the core, and then we'll talk about the windings in a little bit as well. So A and C phase should be comparable, and then B phase should be a little bit different in this low frequency region. The next test that you can do is what we call an end-to-end short circuit test. And so I guess one thing I'll mention is on the end-to-end open test. We call it open because every other connection or every other terminal on that transformer is left open. You don't have anything shorted, you don't have anything grounded. You're only connecting to those two sides of the winding on opposite sides of it, and everything else is floating. The end-to-end short circuit test is really repeating that measurement, but at this point now what you do is you short off all the secondary. So you still do the same thing you did prior as far as connections go, but now you short the secondary winding. And I kind of see this as shorting out the core influence on there, because you just take that away, so it's easy to determine if there's a change in the response, if it was just because of the core, because this test, takes out the core effects and you don't need to look at it. And then what's nice is as you get to the higher frequencies, it's actually going to be very similar to the end-to-end open circuit test. And then if you look at this, really at the low frequencies, all 3 phases should be very similar, and you really want less than 1/4 dB difference. If you have something greater than that, there might be some kind of leakage reactance or winding resistance type problem there. But you should have a nice flat response going for all 3 phases there. The next test that we'll talk about here is the inner winding test, or the capacitive inner winding. And so at this point, now what you're doing is you're going to apply the voltage to one winding, and then what you're going to do is you're actually going to measure on the corresponding winding on the secondary there, on the same phase, but now you're applying to the primary and measuring on the secondary. What happens is that the low frequencies, it's really dominated by the inner winding capacitance, and then it changes as you go up. Then as we go through, and there's a little typo there that says IIW, but it's really capacitive inner winding, so it should be CIW there. The next one we have here is inductive inner winding. So now, once again, it's a repeat of the previous test you did as far as connections go, but now what you're going to do is you're going to ground the opposite side of that winding there. So once again, inject on one side of the winding on like primary on A phase, and then you're going to ground the opposite side, and then you're going to measure the response on the A phase on the secondary, grounding the opposite side of that winding. So, and the nice thing about this is at the low frequency range, you can really see the turns ratio of your transformer. And this is similar if you've ever done your TTR with your power factor test set. So looking at this, you have your capacitive inner winding, which is kind of, the capacitive effects of the winding interaction there dominates the low frequencies. And then you have the inductive inner winding where the TTR, the turns ratio affects the low frequencies. And then as you go on to the higher frequency range and the mid to high frequency range, these two guys are going to start to overlap, and you'll see a very similar response, or you should see a very similar response in a typical result. So now that we've kind of gone through the four basic types of tests you can do, really these are all types of tests we've done with other test equipment before. If you look at it and you see, okay, what about our open circuit self-admittance test there? We're energizing one side of the winding, and we're measuring the response on the other side of the winding. And so if you think about it, and this is looking, of course, at the windings and the core characteristics, but really this is similar to your excitation test that you would do with a power factor test set, where you're just seeing how much current it gets to excite that winding. But now what we're doing, instead of doing it at a high voltage at one frequency, we're doing it at a low voltage at a wide range of frequencies. And then now the next thing is the short circuit self-admittance test. This once again looks at the winding, because if you think that shorting shorts out the core effects of the response there, this is really basically your leakage reactance test again, where now you're hooking up, you're going through the winding, you're energizing one side of the winding, you're measuring the response on the other side of the winding, and then you just short out the secondary, and you can look at the leakage reactance of this transformer. And then the next one, of course, is your capacitive inner winding, where now we're once again energizing one side of a winding on the primary, and then we're measuring that corresponding phase in that part of the winding on the secondary there. And really this is looking at the capacitance between the windings, but if you think about it, it's your capacitance test, your typical power factor insulation test. But once again, we're not really stressing anything here. We're not putting a high voltage on there at one frequency or a narrow band frequency. We're actually going at a very low voltage, but we're going over a wide range of frequency from 20 hertz to 2 megahertz there. And then the inductive inner winding, once again, it's similar to the capacitive inner winding, but now we're grounding off the opposite portion of that winding there. And then it kind of looks at the inductance of both windings. And it's similar to your TTR test, which if you've ever done a TTR test with your power factor test set where you use that reference capacitor, you can actually, once again, that's at the 60 hertz measurement. This is over a variety of frequencies, but if you look at the low frequency response on this inductive inner winding test, you can actually see and calculate the turns ratio of your transformer. So now there's four types of tests, But the difference here compared to some of the other ones, like we're in power factor, where you actually go through and you just do one overall bulk insulation test. This you're actually doing everything by each winding. So let's look at the first kind of 3 tests that everyone does on the transformer. Your open circuit self-admittance test. So what we're going to do is we're going to go through, we're going to do apply a signal to the one side of the winding on the high voltage and measure the response on the other side of the winding. So we're going to do that for A phase, we're going to do that for B phase, and then we're going to do that for C phase. Then those are our first 3 tests. The next thing we'll do is we'll actually short off the secondary, and once again just repeat those tests. And this is the short circuit self-admittance test. So same connections on the high side, apply a signal to the A phase, and then measure on the opposite part of the winding, and then do the same thing for the B phase and do the same thing for the C phase, and just have the low voltage terminal shorted this whole time. And generally what a lot of people will do in practice to make it quicker is I would start with A phase and have my leads connected here and go apply here, measure here with everything floating, nothing else connected. And then what I would do is I would come over here and short the low voltage terminals and then apply the signal and measure through here. And then I can move my leads and go through B phase with these shorted and then go back and unshort while I'm connected to B phase. And then I would move to C phase, do that test, and then short again, just to save a little bit of time. And I would say the nice thing about the SFRA is the actual test time is pretty quick. Ours goes out in about 45 seconds, you get a response. But the connection is what takes the main amount of time, because you got to go to the different bushings and you got to ground everything out and be careful on your connections there. So now what we've done is we've done your open circuit test, your short circuit test, and then you'll go through and you'll go on to the low side now, and you'll do your open circuit test on the low side with everything else floating. So once again, apply your signal on your one side of the winding on your A phase and measure it on the other side of the winding on your low voltage side with everything else floating. Then once again, you'll do this on B phase, and then once again on C phase there. So now we have our 9 basic tests. We have our 6 open circuit tests and then our 3 short circuit tests. And then the other ones that you want to do, of course, is your capacitive and inductive interwinding. So once again, your capacitive interwinding is similar to your power factor, but phase by phase now. So you apply on one side of the winding on the A phase, on the high side, and then you connect on the same point on the low voltage side, or the secondary on the A phase there, and measure there. And then you do that for B phase, and you do it for C phase, but everything else is left floating. Then when you go to the inductive interwinding, once again, we're going to do the same test, but you're going to ground the opposite side of those windings there. So now applying to the or to one side of the A phase, grounding the opposite side of the primary A phase, and then measuring on the corresponding low voltage or secondary A phase and grounding the opposite side of that winding. And you'll go through and you'll measure that on B phase and on C phase as well. Then what happens is at the end, we have our 15 basic tests, kind of your 9 core tests or your 9 standard tests, and then I would say your 6 extra capacitive and inductive interwinding tests there. So when we combine all these, this is a typical graph that kind of looks like a piece of modern art here. So you just have a series of squiggly lines across the whole panel. And then at this point, the nice thing is to have a good software where you can easily turn curves on and off just to view what's going on. And so remember, the actual device itself just did the same thing every time. It applies a voltage, a 10 volt signal at a varying frequency from 20 hertz all the way up to 2 megahertz. And then by changing our connections, shorting something out, grounding something out, we're actually getting multiple different responses for that particular transformer. At the end, you'll get something like this for your fingerprint of a typical 2-winding transformer there. So when do we run these tests? So what I generally recommend is when you're doing an acceptance test or a commissioning test, or if that transformer has been sitting there for a while and you don't have any previous measurements, so you just want to get your reference or your fingerprint, you're assuming it's in a known good condition here. So you want to run all 15 sweeps at that point. 6 open circuit, 3 on the primary, 3 on the secondary, 3 short circuit where you measure on the primary and you short the secondary, and then 3 capacitive interwinding and 3 inductive interwinding. Then later on down the road, you're just doing a quick check, like a preventive maintenance or something happened, you might want to check on the transformer. You might just get away if you're limited on time running the 9 sweeps, your 6 open circuit and your 3 short circuit. And so if those line up, I would say mechanically, physically, nothing changed in that transformer. But if something happens and there was a fault or you transported the transformer, there's some kind of suspected problem, this is where you'd actually want to run all 15 of the sweeps there. So when do we get our reference measurements? When the transformer is new, and this of course is the best time, when that you first get it, you're doing your commissioning, and you just want your reference to use for future measurements. Now the problem is this technology is, I would say, fairly new in the industry, maybe a little over a decade or so, and then just over the last 5 or 6 years, there's guides out and everything from IEEE. So you might not have your transformer new fingerprint, but what you can say is, okay, this transformer's out there, it's passed all our other tests, so it's in a known good condition. So let's go out and at least get our fingerprint from there. So there might be something, that it like you don't have a previous measurement to compare it to, but at least you have something now for future reference in case something goes wrong with that transformer. So really, the thing to do is start making your measurements on the transformer as soon as possible. Brand new one, commission it, and then if it's been in the field for a while, just go out there on the next test and get that information, because if something happens, it's nice to have that fingerprint for comparison. So when are these being performed? I give our recommendation here, but what's going on a lot of time is during manufacturing, they'll do this. They'll make a measurement just so when they go to transport it and it goes out, they'll actually have some kind of reference to compare it to. And then, of course, commissioning test. So when you get it on the pad, put it on there, and you want to make sure before you energize, you have all this on the fully dressed transformer. And what I've seen a lot of times is that what they'll do is they'll go through and they'll do their SFRA measurement at the factory with transportation bushings and different things on like that, and then transport it along, and then maybe set it on the pad and run through and do an SFRA measurement again to verify nothing happened during transportation. Because if they go through, assemble the bushings, pull vacuum, fully dress the transformer, put oil in it, and then at that point they find out there's something wrong with the transformer, they wasted all that time putting into assembling the transformer when they would have seen it right away with a quick SFRA test in the beginning if something happened during the transportation process. The other times that you'll see it, if there's a short circuit fault, some kind of earthquake or hurricane, something like that, or maybe you had the transformer trip off, or you had some kind of DGA analysis, high temperature, different things like that, you may want to go in with further investigation, and SFRA is a nice tool. So one thing about the sweep frequency response analysis is that it's really a comparative test. What you want to do is you want to have your known fingerprint, and then later on run the test again and compare it to your original fingerprint there. So the best thing you can do is a time-based test, where it's the same transformer, you have your fingerprint, then later on down the road, if something happened, you suspect a fault, something like that, you test that transformer again, and you compare it to the original. But as we said, you don't always have a previous measurement. So what you may have to do is look at a type-based test, where now you have 2 or 3 of the same transformer with consecutive serial numbers there. And so you go across and you measure, the transformer 1, and then you measure transformer 2, and you can compare those to each other and see if they line up and are similar. Then the last thing you can do if you don't have a previous measurement is do a design-based test, where now it's like, all right, I can compare all 3 windings to each other. I can look at the A phase response compared to the C phase response and different things like that in the core region. And then as you go across the windings, all 3 of them will line up. So you have different tests you can do depending on the information that you have, or different comparative abilities depending on the information you have. So if at all possible, that the time-based test is the best test. It's the most reliable because all right, I had this previous one, this is what the curve looks like. And as far as I'm hooking up the same, my tap chains are in the same position, connections are the same, and I run this test again, if I see any kind of deviation, I know something mechanically changed inside that transformer. Then the next thing is the type-based test. So this is where you have a twin or sister transformer. Okay, I have transformer 1 and transformer 2. And so if I get a response on transformer 1 and transformer 2 looks the same, it's like, okay, these 2 are both in good condition. Now, if there's a little bit of difference, it could be just that there was a slight difference in the manufacturing process, or it could be that there's actually a problem with the transformer. So small deviations don't necessarily indicate a problem, but large deviations you're going to want to look into. And when I say sister units there, I mean basically consecutive serial number and same design, same manufacturer. Even if I came through and I said, all right, this one's transformer A is, this impedance, this voltage, this kVA, and transformer B is the same, but they're 2 different manufacturers. Those aren't going to be comparable results because they're not true sister units. Then, as I said, the last thing is a design-based test where you're going to compare the phases to each other and see what's going on. So same thing, small deviations aren't necessarily a problem. It could just be based on the design. But if you do see like they line up to each other, then you've got a good transformer there. Like physically, mechanically inside, they are both, the windings are similar and doing well. So what do we do with all these results? Really, it's pretty simple, like in the basics. You go through, you take your new measurement, you compare it to your reference measurement. If they overlay, they line up. Really, there's no mechanical changes, no physical changes inside that transformer, so put it back in service. Now, if you take your new measurement, compare it to your reference measurement, your fingerprint, and they don't line up, now something physically or mechanically changed inside that transformer, and further diagnostics are required there. So let's look at a little example here. So a time-based comparison. We had the same transformer, and we went through and, on commissioning, we ran a test, and then later on, we went back at a different date, with an SFR unit again, and ran the test again. So basically, same conditions, same unit, same connections for both tests, but just at different times. And so just so you know, any additional component will influence the measurement. So if I had the tap changer on, raised 16 at one point, and I'm measuring again on raised 1, it's going to be different. If I change the oil, if I have different bushings on, this is all going to change the result. So really on a time-based comparison, you want to make sure everything's the same. And as I said before, it's an offline test. You want this thing de-energized. You want all the bus connections taken off because those can influence the test as well. So really for a time-based test, you want everything the same. So let's look at this. We have our original fingerprint from commissioning, and then there was a fault on this one. So you want to compare the two and overlay them. So if I do that, we go through, and now you can see there's actually a deviation here between it's the same phase on the same transformer, same connections, but you see these no longer overlay. So something happened during that fault, and now we know that the actual transformer, something mechanically changed internally in that transformer. Then next thing, of course, is the type-based comparison, where you have two similar transformers that are consecutive serial numbers or close to each other there. And so what I mean by that is you could even have serial number A1 and then an A2, and those are comparable, or A5 and A6. But you might not necessarily be able to compare A6 to A1 as well, because if these came off the assembly line at different times or had like a year or two delay between the manufacturer, they could have changed materials a little bit and changed the design slightly. So really you want nearly consecutive serial numbers, same manufacturer, same factory, and same technical specifications. So as I said, if you go through and you don't, if you have the same impedance, the same voltage and everything, and the same power rating, but it's one's manufacturer A and one's manufacturer B, these aren't going to be sister transformers. They're going to have different responses. They'll all have like a typical looking response, but you won't be able to overlay and compare them. And then, of course, the design-based one is now, once again, you're looking at there and you're comparing A phase to C phase, and then on the windings, A, B, and C phase together in the winding region of the curve. But this is when you have like a three-phase type transformer all in one. And basically, any kind of mechanical defect, a slight one might just be due to manufacturing and the transformer is okay, but if you see large deviation, then you look into it and you see, okay, something's changing within our transformer. But it's really, each one has a little bit of a confidence level there. So a couple things to look for on a design-based comparison. On your open circuit test, if you look down in the core region, what you'll see is A and C phase will be very similar, or should be very similar, and overlap each other. And you have this typical double dip response here, kind of how each the two outside legs respond the same, and then you have that single dip for your center leg. And once again, this open circuit test is comparable to your excitation current, where now you have two outside legs that are similar currents, excitation currents, and then that center phase, which actually is less current that it takes to excite it. So it's that typical, or it's that same type of response, and why you have this symmetry between two of them and a little difference between that single one. Then, of course, we go through and we do our short circuit test here. And now at the very low frequencies, you want these to overlay and have very little difference between the phases. And then, of course, as it goes higher up, you're going to, hopefully, the three phases will overlap each other as you go to the higher frequencies. So at your basic 9 tests here, you're going to have your 6 open circuit test, your low voltage open, your high voltage open, and then your high voltage short there. And so you get this typical response there, and you can kind of do a phase comparison. So things to look for is on the high voltage, you're going to have basically that double dip response. on two of the phases, and then that single dip on the center leg on the low frequencies. And then as you get to the higher frequencies, the three windings are going to start to overlap each other. And then as you look at the high voltage short, you'll see all three will be the same coming down through the low frequencies, because you're shorting out those core effects. But then as you start to get to the high frequencies, they're still overlapping each other, and they're actually going to start to align with the high voltage open response. And then of course the low voltage open, once again, you're going to get that double dip response for the two outside legs, and then for that center leg, you'll get that single dip. And then as you come out of there into the mid to high range frequencies, once again, all three phases should overlay each other. And so this is once again just your kind of phase comparison and what to look for when you first do the test. And so now you'll see some minor differences between phases, and that's not necessarily an indication of a problem. And so, as I mentioned multiple times, you really want a fingerprint. You want a reference measurement for this. But when you don't have it, you want to compare the phases and look at it. And small deviations are acceptable. And just to give you a reference point, this is what a transformer will look like that actually had a serious fault internally. And this is your three-phase comparison here. So you'll see it's not like they deviate a little. There's serious deviation between the windings here. And so a typical one, everything's going to line up. Of course, your low side tests and your high side are going to be different, but all the phases are going to be quite comparable there. Whereas if you look at a transformer with serious issues, you'll see there are generally big deviations in low voltage and mid and high range frequencies. So looking at this, as I said, the best thing you can do is a time-based comparison where you have a good fingerprint, and then you come back later and you're actually comparing to the same connections on the same transformer. So if you see any kind of difference in the reference trace to your new trace, physically, mechanically, something changed inside that transformer. Now, if you go to your type-based test, where I'm comparing twin transformers, two consecutive serial numbers, or maybe you have three single-phase generators to step-up transformers or something like that, if there's slight differences, you're not quite sure that might be an issue, or it could just be a little bit of the manufacturing process and design process there. But if you see everything line up, then you're comfortable that physically, mechanically, they're all kind of the same or in good condition, I would say. And then a little bit less, confidence level is that design-based test where you're looking at A, B, and C phase. And the thing to remember is it's only when you see deviations that you're not quite sure. If everything lines up good and is very similar, then you're pretty sure that transformer is good. But if there's slight differences, it might just be design effects. If there's large differences like that previous slide I was showing you, then once again something's wrong with that transformer. So once again, we're doing multiple tests: open, short circuit, capacitive interwinding, inductive interwinding. But really, there's a lot of different things can affect the test. If it's a delta winding or a Y winding, of course, the response is going to be different. Things to look for are going to be, resonance shifts, additional resonance or resonance or loss of resonance, and then an overall magnitude difference. Any major changes in that, something's going on inside that transformer. And then once again, remember, the SFRA device is only doing one thing each time. It's just where we connect and what we look at that we actually influence the result. So a couple things to remember here. Comparison is the best method. If you want your commissioning results or the manufacturer test results, and then you want to compare your new test to that one. And if it's on the same transformer, you have good connections, solid connections, you're in the same tap changer position, all that, you overlay them and they're the same, you know that transformer's in a good condition. If you overlay them and they're different, you know that physically, mechanically, something changed inside that transformer. And then one thing I'll mention is repeatability is very important. You want to make sure that you're doing multiple things, that you're, you know, a high quality, high accuracy instrument, of course, but then you're using the same applied voltage for all measurements. If you have a different voltage that you're applying, this could affect the low voltage, the low frequency measurements, because the core takes over at that point. And then you want to make sure you have good solid connections. You're using the shortest braided ground method, so your connections are always solidly connected and the grounding is the same. And then also just good documentation. Make sure you note the tap position. Make sure if you didn't have oil or you had test bushings in there. You want to make sure all that's noted, so if there is a difference, you can see, no, we actually changed the parameters here. We're not measuring, we're not comparing apples to apples, so you're not throwing yourself off there. So looking at this, as I said, we really want comparison and repeatable results. So what are some tips that we can do for field testing there? So first thing, let's think about the test instrument setup. So as I said, you're going to hook up to one side of the winding, use your shield coax cables, apply a 10-volt signal, vary it over multiple frequencies, and measure on another part of that transformer there. And then put this information on a PC, and you can evaluate what's going on. So the first thing to do is just verify your instrument's working. So there's a couple things that you can do. One is have a reference here, like some kind of verification over the whole frequency range and a variety of decibel responses. So you have this known response, and this thing, if you go through and you get the same response, your equipment's doing well. If for some reason you forgot this thing, there's some other tests you can do too to check. One is shorting the leads together, and then you'll expect this typical 0 dB response. So very little change between the output and the input, especially when you look at the full scale here. And then the other thing you can do is an open test, just to check the noise floor of your instrument and see, okay, if we keep the leads open, don't connect anything, where are we getting noise here? And you just want to make sure that's well below the range that you're measuring on your transformer. The next thing you can do is make the test quicker. As I said, one of the difficulties or the slow things about this is the connection, but you also need to sweep through multiple frequencies. And so with ours, it's generally about 42, 45 seconds to run through a sweep. The reason is because we are smart about where we measure the data point. So as we're in the low frequency range where it's a nice smooth curve and you don't need as many, we'll take a few less data points. And then as we're going through into the mid-range frequencies, we'll increase the number of data points. And into the high-range frequencies, we'll really start doing a lot so we can get all the little deviations in there. And this helps you speed up the test so you're not waiting around if you're doing the same points per division at every frequency range. So lead placement. Just looking in the software, what's nice is it indicates to you where to connect everything. As I said, once again, the SFRA, the FRAX here, it only does one thing: outputs a voltage at multiple frequencies and measures the response. What your job is to make sure you're connecting it up. So what you do is you look at what we say and you say, okay, the first column there is where we're going to put the actual signal. So if you look at the top one, H1 to H3 open. So we're going to apply the signal to the H1, and then we're going to put our measurement lead on the H3, and then open means everything else on that transformer is floating there. So then we'll do H2 to H1, H3 to H2, and then we can go down and do the secondaries, X1 to the neutral, X2 to the neutral, X3 to the neutral, and those are all open circuit tests, so everything's floating. Then we can go back and do H1 to H3 again, but short X1, 2, and 3 together. And then once again, with these shorted, with the secondary shorted there, you'll actually do H2 to H1 and H3 to H2 again. And once again, if for quicker testing, what I've mentioned is you might want to do H1 to H3 open, then short the secondary with H1 and H3 still connected, run that test, and then switch to H2 to H1 with everything shorted, and then switch back to the open and go back and forth there, just to speed up testing a little bit if you would like. The next thing, and this is very important, is the tap changer position. One thing about SFRA is it's a very sensitive test, which is great because you'll pick up little problems inside your transformer. But the other thing, because it is such a sensitive test, you can actually influence the results, and anything you do can change the results as well. So you want to make sure that you're always indicating, like in your test report, in your test file, what the tap changer positions are. And what you want to do is, if it has a de-energized tap changer, you want this either in the nominal position or in the position that it's going to be in the field there. So then if you pull it out, you don't have to move that tap changer at all. And then the LTC, of course, this is varying during the load while the transformer is in service, so you never know at what point that's going to be. So what you recommend there is to perform this test when the LTC is in the highest raised position. This way, every single tap's in there. And then if you do choose to do it at a nominal, so you can get every tap in there and take them all out, just note which positions you approached that nominal from. If you come from raised or you come from lower, it can actually influence the results. So you want to make sure that you not only indicate the tap position, but how you got to that position as well. And just note this in the actual test file there. The next thing, as I mentioned, once again, you can influence it. Your connections will influence the result. So bad connections can actually vary the result too. So if you look at this, this is actually the same transformer taken at two different times, and it's the same phase, it's the same measurement, X1 to X3. So we energized on the X1, measured on the X3, and everything else is open. But you'll see there's a large deviation here in the very high range frequencies. Well, what it was is this was a bad connection, and this was taken at first with a typical like alligator clip, like jumper cable type clamp. So if they actually went back and cleaned the connection, made sure it was a good connection, and now you can see once again these pretty much overlay each other. And this is why you want a nice good connection, use like a C clamp that you know when you go down, it's connected, you're solid there. And from this, you can actually, I've seen some people, they'll actually go through and measure the termination impedance there to verify their connection. So continuing with connections, not only are you solid connected to the terminal where you're injecting and measuring, you also need to ground off these devices. And so we isolate, because it's that coax cable, you want to isolate and ground off this connection as well. And the best thing to do is use what we call the shortest braided ground principle. So you have a braided ground that goes down, and then you have a little clip to make it adjustable. So if I have a really long bushing and I have a bunch of extra grounding, I just clip off to the part I want, and I make it kind of taut to the closest ground connection I can go to. And this will allow you to be repeatable each time and make sure if I do it, if you do it, if someone else does it, we're going to have a different connection. I mean, we're going to have the same connection and the same grounding point. So if you look here, you have this nice long piece here, and it can go way past it, but then you have the short connection point to go to your quickest ground. So if it's a short bushing or if it's a long bushing, you're still always grounding at the same point, and you're going to the first ground you can get connected to. So looking here, preferred grounding practice, shortest braided ground. Poor grounding is when you just have ground floating around, and this could be curled up or this could be laid out flat. And because the inductance of that loops change or the impedances change, it'll vary the results in that high range frequency. So by doing the shortest braided ground, having solid connections, you're going to have repeatable results there. Then one thing, and this is always mentioned, whenever, typical IEEE recommends doing your winding resistance test last, and also demagnetizing after you perform the winding resistance, because an actual magnetized transformer will change the response in those low range frequency, because you've magnetized that core and it's not going to behave the same since you're just putting a low voltage on there. So make sure that if you go through and you do your winding resistance, you demagnetize. But really, before performing winding resistance, you would want to perform this SFRA test, so it doesn't affect the results there. Then another nice thing to have is a little built-in support within the software, where you can actually look over two different responses, your original and then your fingerprint and your new test, overlay them and see, apply a couple of algorithms and see if there's any distortion within that. So built into the software, that helps as well. So a couple of things here, just in summary. The nice thing about SFRA is it's very sensitive, and you can see a variety of things with it. All these different problems with core and winding and taps and connections. So one test or series of tests with one instrument will get you a lot of information about the physical mechanical condition of your transformer. It's just one piece of the puzzle, right? Because you still need to do insulation, DGA is good, but really this gets an overall physical mechanical condition of your transformer. But being a sensitive test, repeatability is really highly important. So you want to make sure you're always connecting the same voltages, good grounding practices. You're noting the tap positions and you're testing in the same tap positions as well. And really, comparison is the best method for evaluation. You want those reference measurements as soon as possible upon commissioning or in known good condition. So later on, if there is kind of fault or suspected fault, when you do the new test, you're doing a time-based comparison and you have a known reference for that particular transformer and you're overlaying the other one and you want them to line up. If not, you'll have to look at a design-based test or a sister comparison, something like that. So this is like a general intro to SFRA. Some further reading I would recommend, of course, is the Gray brochures 342, and then of course the IEEE guide 149 or 57-149. And then just to mention a few things, of course, we talked about how to use it. This is our device, the Frax 101, a nice lightweight, very rugged for field use. This is battery operated. You can control with your computer. You can actually connect via USB or via Bluetooth. You could run out with, charge this thing up and have no power out there and still run your test. And what's nice is the highest dynamic range and accuracy in the industry, and very simple software and easy to use. And it comes in a little pellet case. You have your unit, you have your leads, you have your laptop, you can run and test the thing. And then if you don't have a laptop or, IT's got you locked down, we also have the Frax 150, which is basically the same thing as the Frax 101. It's just a little bit bigger because we put this nice PC embedded and touchscreen on there. But other than that, it's the same specifications electrically wise of the Frax 101. Same high dynamic range, simple software and everything. And then a couple accessories, as I mentioned, you want a known reference. So the field test box comes standard with all the Frax units, just to verify the instruments work in all frequency range. And then we also have an optional accessory that's the field demo box that you can use as a training tool, and you can simulate a variety of things. You can mess with the core, you can clamp a winding down, you can short a winding, you can lose turns, different things like that. One other thing I want to be mentioned, so thanks for attending this webinar today. But I also want to mention we have these different MEGGER transformer life management bulletins, and so far we've had a variety of them: moisture and power transformers, LTC testing, what ITC, individual temperature correction is, winding resistance, core DMAG, a bunch of different things are available, and you can just kind of download these at your leisure. If you see this, if you go to MEGGER and look for the Transformer Life Management Bulletins, you can use this link here, and you can download these. And it's a nice intro to a lot of these topics, and some actually go into quite the detail. And the next one to actually be released will be on SFRA. And so we'll go through the introduction and then talk about the transformer, and then what does SFRA detect, and some typical responses, how to perform the test, some analysis, some examples, and when to use SFRA. So if you get a chance, sign up for these bulletins, or just go down or go to our website and download them. And if you want more info on SFRA, look into this. And then of course, we'll also in these bulletins reference other papers for further reading if you would like. And then at this point, Jamie, I'll turn it over to you for a minute before we go into the panel session.
Okay, thank you, Robert. At this time, the presentation portion of the webinar is officially concluded. We're going to go ahead now and take 30 minutes to answer as many of your questions as possible. And we've already had a lot of those come in already. But if you do have any other questions, you could go ahead and submit them now into the Q&A box on the right side of your screen. Just be aware that we probably won't get to all the questions today, but if we don't, we will be sure to answer those in the next couple of weeks. We'll get to you through email to make sure those are taken care of. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. And on the survey, just be aware there's a field where you can also request a demo or quote or on any MEGGER products as well. And just be aware a copy of the presentation along with a link to the video recording of the webinar will be emailed to everyone within about 2 to 3 business days. Another thing, you can also view previous video recordings of webinars on our website at us.megger.com/webinars. And you can also register for next month's webinar, Fault Location on Oil Field Cables, which will be on March 16th at 10 a.m. Central Standard Time. And the presenter for that webinar will be Robert Prost. He's a MEGGER cable applications engineer. And we'd also like to make you aware of some great power transformer hands-on courses from AVO Training Institute. You can visit avotraining.com to view their upcoming schedule. They have 4.5-day transformer and advanced transformer maintenance testing courses, and those are also available in Spanish. AVO's been training for about over 50 years and has some of the most knowledgeable instructors around, so definitely recommend checking them out. And one more thing before we get to your questions. If you're planning on attending a NETA Power Test in a couple of weeks, we'd love it if you could stop by the MEGGER Hospitality Suite in Magnolia Room 3. That's on Monday, February 26th from 6 to 10 p.m. We're going to be giving out a lot of great prizes and should be a lot of fun. We'll also invite you to stop by our booth on Tuesday, the following day, booth number 301. That'll be open at noon. And then we'll also be hosting the MEGGER Spotlight Stage presentation at 3 p.m. So invite y'all to come check that out if you're going to be in town for NETA. All right, now let's go ahead and get to some of your questions. First question was asked by Jim Lyle. He asked, several of us who have joined today are from the generator world. So if you have thoughts on how this might apply there, I would appreciate your input. Go ahead and give this one to our panelist, Diego.
Well, good morning, everyone. This is quite an interesting question because generation is one of the main operational critical components of the system. And when we're talking about generation, we have to remember that most of the transformers working on the generation system are loaded close to 100%. So you have a constant load to your transformer, and the biggest short circuit current that you can see on the electrical infrastructure is most of the time on a three-phase fault, and the three-phase fault is typical mainly on generation side. So when the fault hits you guys on generation, that's really going to shake your transformer. So that's one of the things that you have to keep in mind. So this does apply to you guys. And remember as well that most of the transformers that you have in your facilities are designed maybe on a shell type and are pretty robust. Take care of those and make sure that the loading process, of course, will influence. And as I said, if you have a fault, that one is going to be the biggest one for your transformer windings if you are close to generation and you have a three-phase type of fault.
All right, thank you, Diego. Next question was asked by Wallace. Is this test better with the transformer fully disconnected, or can you do it with it connected? And go ahead and assign this one to Volney.
Okay, so definitely the transformer has to be disconnected, fully disconnected. Anything that is connected to the terminals of the transformer will be influencing the response you get from the test. So unless you have some big difficulties to do the disconnection, the best thing is to run the test disconnected. And if for any reason you have to run the test with the transformer connected, make notes and full documentation of that, so whoever runs a test knows and understands what he might be getting. So that will be for that question.
Okay, thank you, Volney. Another question for Diego. This was asked by Abel. Can pattern recognition be used to identify specific types of faults given a specific suite?
That is a quite interesting question, because most of the time when you have a fault, there's no one specific pattern to follow. When you have a fault, you may have a winding deformation, you may have some issues with insulation, you may have a winding elongation, you may have a buckling, you may have all of them together. So under the experimental side, if you look into the reference provided by IEEE C57-149, which is, I think, one of the best documents given for interpretation of results, you will see that, yes, there are different patterns, and most of them are shown in the way of an end-to-end open circuit or short circuit test, and you can do some sort of analysis. But when things happen in the field, you will see that most of the time it's not just one thing happening. It's not just deformation. It's not just elongation. You may have as well as short circuit in your turns. So keep that in mind.
All right, thank you, Diego. Another question for Volney, asked by CS. What is the range of frequency in the short circuit traces? Should we check to verify if the healthiness? Should we check to verify the healthiness of the winding?
Okay, so one thing to consider when we are running the short circuit test or connection, we are taking out the effect of the core. So in that case, we're going to see basically the response from the winding, and that should appear from the mid frequencies up. So we are evaluating the winding, and in some cases, you would see if there's any winding resistance difference. You're going to see also effect of that in the response in the very low frequencies. That is something that you can use to evaluate the winding resistance of the transformer.
Maybe I can add a little bit on that one. If you look at your short circuit impedance kind of test, and you look at the short circuit response on your sweep frequency, you will see that the very low frequencies have to match the three windings. Okay, and you will see that the response is very close to 0 decibels. That is a pattern to follow. And then when you go beyond maybe say around 100 kilohertz, you will see that now the windings are reflected and the response is very similar to your open circuit. So that's kind of things, little things that you have to look at on your short circuit response.
Okay, thanks, guys. Next question is for Robert, and Eric asked the question, for the factory test, can we compare with a different tester on site?
So I would say with that one, there's a couple things to consider. I mean, it's almost yes and no here, because you can use different testers, but you want to verify a few things. One, that the output voltage is the same So as long as we have the same output voltage and we're running along the same frequency, they should be pretty much comparable. The only difference that you'll see is also with connections, because what happens is, say if you're making your connections and one unit's not using the shortest braided ground principle and the other one is, you'll have a little bit of variance there. And basically, if you're not repeatable on your connections and your measurements, even if you're using just your own kind of grounding method, and then you go through and even you use that device again and your grounding's not the same, it can vary in those high frequencies. But if you're using the same voltage, same connection, same grounding, you can use instrument A and instrument B, and they'll be comparable with each other there, as long as those voltages and connections are the same. And of course, other things such as note in the factory, if they're doing a test prior to transportation, they might have actually drained the oil out, or they might have used test bushings and different things. So you want to make sure that's noted. But as far as using, one manufacturer's instrument and you're using yours, as long as you're using the same voltage and the same kind of grounding practices, you're going to have the same results there, as long as nothing happened within the transformer.
Okay, thank you, Robert. Next question is for Volney, and it was asked by Jutian. What software is needed to view the test results? And part two of the question is, do we need MEGGER to interpret the testing results comparison, or can the software diagnosis and provide, say, if we compare two different tests on the same transformer?
Okay, so several things here. First of all, each manufacturer will have its own software, so it's good to verify if that software is able to read files from tests run with a different manufacturer. In our case, we definitely can do that. We can read all of the software, all of the manufacturer results. Second thing here, if you don't have our instrument, we also have a viewer, just something that you can use to see all of the type of files that are out there that can measure SFRA or can do SFRA tests. And then the third thing, and talking about our software, in our software we have, for the analysis, we have different tools. So the first tool that we have is the difference. So you can compare two different traces and the software will calculate the difference between them, and you can see if there's a difference in magnitude, difference in frequency, or difference in phase as well. And then the standards that Robert was mentioning, the IEEE standard, the DLT standard, they have some methods to compare and to some statistical methods to analyze the curves and the comparison of the results. We have these methods implemented in the software, and the software will show you if the comparison has notorious differences, or if there's no change in the plot based out of the evaluation that is recommended in the standards.
Okay, thank you, Volney. Next question is for Diego. Syed asked, is interwinding test same as C and DF test?
Okay, when we're talking about interwinding capacitive test, we are making a reference that if something flags up during the interwinding capacitive test, you may correlate and you may try to correlate results with a capacitive and power factor test. Now, you need to understand that the way we're looking on SFRA is different to the way we're looking in a power factor test. When you do a power factor test, you will short the windings, right? And you will basically create one single electrode with equipotential energy, right, or electric field on all three phases at the same time. In this case, we're looking at winding by winding. So when you do your power factor test, basically it's an average situation, and you cannot pinpoint where the problem could be. But now, if you had a pattern and you had a benchmark of each of the windings going phase to phase on this capacitive interwinding, then you might be able to better identify the location of a potential fault with your throughout the capacity geometry of the winding. So it's a little bit different, but we're looking at the capacitive component anyway. Remember that when we're doing this test, we're still thinking about an RLC circuit. So there's a little bit of differences here.
Okay, thank you, Diego. Next question is for Robert. Zachary asked, how long should we be allotting, or how long should we be allotted to perform all 15 SFRA tests?
And I guess this is a little difficult question because it depends on the transformer size and everything and the crew, of course. But what I found is, once again, you need the transformer de-energized, fully disconnected, all the bushing off. But once you're at that point, if you're, say, at like a, maybe a 121 kV or 245 kV transformer where you can get to the bushings from just standing on top of the transformer, you could really do this test, all 15 of them, on a 2-winding transformer in I'd say 45 minutes to an hour. But that's, of course, the transformer's already isolated and everything like that. Well, the problem is, say if you start getting up to 362, 500 kV and beyond, now it's not as easy to get to the winding or to the bushing terminals. You're going up with a man lift, making your connections there. So it just takes a little bit of time. Really what you need to do is you're clamping to one at the top of the winding and then grounding that off. You're doing your shortest braided ground connection and then going to another bushing terminal there. And the sweeps itself only takes less than a minute each. It's really the connections that take the time. So I would say with a smaller transformer, just testing time you can get done in like 45 minutes, and then maybe double that as you start to get higher up and you need a man lift to move around the transformer to make your connections.
All right, thank you, Robert. Next question is for Diego. What is the range of the frequency variation that shows abnormality in transformer?
This is a very interesting question, Jamie, and I appreciate Sayed for asking that question. Well, let me put it this way. When you look at the transformer and you run your test from typically 20 hertz all the way up to 2 megahertz, the reason for going on that window by all the standards, and remember that before, some time ago, when this technology came out, there were different suggestions about the frequencies that need to be used. Somebody said go all the way up to 2 megahertz. Somebody said, no, we don't need 2 megahertz. Let's do only up to 1 megahertz. And at the end, I think that with the latest standards from IEC and IEEE, the idea is to have something that everybody could compare. And we typically go from 20 hertz all the way up to 2 megahertz. Now, one of the interesting things about this is on IEC document, on the standard from IEC, you will see that they suggest to run a zero check test. What is interesting here is that by connecting the input and the output of your SFRA on the same bushing, basically you should see a voltage output versus voltage input and showing you the same voltages. Therefore, if we go into the magnitude equation, that would be a logarithmic for unity, and that equals to 0. So you should see a 0 response all the way up on the transformer response. But when you come out from the 0 line and you start looking into some distortions and deviations greatly visible on your response, that might be resonance from anything else but your transformer. So if you really want to look into your transformer, just run this zero check test on your transformer, look into the standard from IEC part 18, and you can define, because every transformer, every design has its differences, and you might be able to see this way a little bit better what is most important for you. And remember that you have your open circuit, you have your short circuit, you have your interwinding testing. So each one provides information on all the spectrum that we're looking, at least between 20 and 2 megahertz. There's good information, and from design to design, there will be different frequencies that will overlap. The standard is flexible when they say, well, from here to this frequency is just the core. Well, it depends a little bit on the type of design. So you have to be flexible and understand better your transformer.
Okay, thank you, Diego. Next question is for Volney. Cole asked, do we need to run these tests on all taps?
Okay, so here the first thing is to divide the question in, or the tap question about, on the de-energized tap changer and the load tap changer. So for the load tap changer, the recommendation from the standards is to run it on the entire, covering the entire winding. That will mean 16 rise, or the biggest tap or highest tap. Also on the neutral position. And there's the recommendation to get to the neutral position coming from the raise position. So this way you will have always the particular connection of the neutral position and then the entire winding on the transformer. It's not bad to run it on all of the taps. You can see specific situations on each tap, but not fully necessary. On the de-energized tap changer, since once the transformer gets in service, you usually don't move that tap. They could have used the transformer in tap number 3, let's say, or tap number 2. And for any reason during commissioning, it was only tested on the nominal tap. So because using or going to a different tap position, you're going to have a different RLC circuit configuration. You are going not to get the same response for the tap 2, and you're not going to have a way to compare to tap number 3. So for commissioning purposes, for the de-energized tap changer, it's suggested to run it for all of the tap positions. So you have all of the winding response and all of the taps.
Okay, thank you, Volney. Next question is for Diego. Jay asked, why not 3 short circuit with primary shorted and measurement on secondary?
Okay. If we go a little bit into the fundamentals of short circuit impedance testing, right? When you look at the nameplate of your transformer and it says, for example, let's say short circuit impedance equals 10%. The meaning of that 10% is that under short circuit conditions on your secondary winding, with 10% of the nominal voltage on the primary, you will create 100% circulation of current on your secondary winding. So the idea normally is to apply very low voltage or very low current from the primary side to make sure that you don't create high current on the secondary. And if you are going from the secondary, and if I understand this correctly, it's going to be your low voltage side, right? The 10 volt or 20 volt that people will be applying for this test may go, beyond a little bit of the limits that you may have for your high voltage side current. So it's safer and it's better just to run it from the high voltage side.
All right, thank you, Diego. Next question is for Robert. Marcus asks, when comparing measured results against the reference results, are there certain trends or characteristics that indicate specific problems? And part 2 of the question, for instance, if the ratio is higher or lower for a given frequency in the winding range, does that indicate a specific problem?
So looking at this, there's a couple things to consider. One, like everything's overlapping a little in here. So we don't have specific ranges for like established range for core, established for winding and everything. But typically what happens is on your open circuit test, when you're looking at the low frequency ranges, that is your typical core result. So you'll see maybe a core connection that came undone, or you might see something like the core's magnetized and different things like that. Then as you move over into the mid-range frequencies, that's where your winding is. And so now it's kind of odd because you'll see that there's an issue with the winding. And now what you do is you look at different results and you'll see, okay, maybe if if we have a frequency shift or like a resonance point shift or loss of resonance, it's indicating there's an issue with the winding. And of course, we have different examples of what maybe like, a hoop buckling or a winding collapse or stretching or whatever. But the problem is generally if something happened to that winding, it's not just one effect. It might have, buckled a little and expanded, the insulation's breaking down. But you're getting an indication that something's wrong with the winding. But you'll see it also, it will overlay into the low frequency range. And it could overlay into the high frequency range as well. And then as you get to the high frequency range, as I said, the windings overlap up there too. But that could also be a problem with a bushing connection in there or a connection on your tap changer. So it's not necessarily that you'll see, I know that, that A phase has hoop buckling and B phase has a collapsed winding. It's really that you see, okay, I have a winding issue with my transformer, so I need to go in and fix that winding, or I need to go in and fix the cord, or there's an expected core problem, or there's a tap and connection, and maybe my connection and my bushing is bad. So it's, and any time you have a problem, it's kind of overlaid on multiple things. Just winding doesn't fail in just one way a lot of times. So you'll see different things. And the thing to look for is magnitude shifts or shifts in resonant points or loss of resonance and things like
that. One thing that I would like to add to what Robert just commented, if you guys do your SFRA test and you get a response, like Robert just mentioned, you may have not just one single type of fault on your winding, and there's many things else. But you need to correlate the test result, okay? If you have some issues or something flags up on your, say, open circuit test, like, you will try to validate that result with an excitation current test. There's people sometimes asking on a seminar, what do you think if I have 2 or 3 decibels difference now on my sweep frequency response, or it has shifted, I don't know, 10 hertz from the original benchmark signature that we got from this transformer. And the main question is, remember that your transformer is under operation and it's facing faults, it's facing transients, it's facing different things, throughout the life. So a little change is okay, and your transformer has been designed to tolerate this type of mechanical, electrical, dielectrical, and thermal stress. So changes will be there, but we need to validate those. So if you did your test and you have some results on your SFRA short circuit, well, if something makes it different, take that information, right? Do the analysis with the analyzer that you have on the software, talk to the MEGGER guys, give us a call, or you can also in the field do a validation. Take your piece of equipment and do your short circuit impedance test and get the results. And then you will see that you have now more information to bring to the table and discuss based on the limitations that we have for each specific test. So if it is short circuit impedance, you can go back to the standard and it will say, well, if you have more than 3% difference, then there's something that you really need to look into that one. But if you get a difference of maybe 1%, well, might be acceptable. So different things that you can do in the field, not just your SFRA results, but your SFRA results will flag up a potential issue. With that information, what is important for you guys and after this seminar is that you are able to validate that information as well with typical routine testing that you do in the field, and equipment that you carry with on every routine maintenance testing that you're doing in the field.
All right, thanks, guys. Looks like we have time for one more question. Last one is for Diego. Henning asked, how is the temperature affecting the test?
Interesting question. Henning, I would say that we're looking at a circuit that is composed of resistive components, inductive components, and capacitive components. Every time we're talking about losses, we try to correlate everything to our I square R, especially when we're talking about thermal response. And when even when we do a winding resistance test, we understand that the resistivity of the material, in this case copper or aluminum, will be affected by temperature. Now, On my transformer, I may see results taken at 85 degrees C or 75 degrees C and reported. But in the field, you might be measuring at 20 degrees C. When you do SFRA, I mean, you will see that in the factory, the SFRA test will be done somewhere close to the 20 degrees C at ambient temperature. And then in the field, if you are running your test between, I would say, 10 degrees and maybe 30 degrees, the influence of temperature is really minor. But if you go beyond that, the effect is more on the resistive component of your winding. So yes, we have seen the influence on temperature, and we have seen that there's small deviation, especially on the open circuit test, especially on the very low frequencies of that. So if we think just from the physics of the materials, it is a resistance, and the resistivity will be affected by temperature.
All right, thank you, Diego. Looks like that's all we have time for today. We apologize if we did not get to your question, but we will be sure to follow up with you offline in the next couple of weeks. I want to thank everybody again for attending, and thank you, Robert, Diego, and Volney for everything as well. All right, you have a great day.
All right, thanks everybody. Thanks, Jamie. Thanks to you guys.